Okay, this is chapter 5. We're going to talk about circular motion and gravitation. And we're going to talk about uniform circular motion, both the kinematics of it as well as the dynamics of uniform circular motion. Objects that are moving in circles, we're going to then talk about highway curves, which can be either banked or unbanked. I'll talk very briefly about non-uniform circular motion and Newton's universal law of gravitation. This will lead us to talk about gravity near the Earth's surfaces, or near the Earth's surface, satellites and the feeling of weightlessness, Kepler's laws. So I'm going to talk about objects that are moving in circles, and if you think about an object that is moving in a circle, kind of going around like that, just a couple of definitions. The period is going to be the time that it takes to do one full revolution, and that would be in seconds. So how long does it take for my object to go from this point all the way around that circle back to that point? That's one revolution. How long did it take? The frequency is equal to 1 divided by the period, and so that would be how many revolutions per second that we're talking about. I highly recommend you take a look at these definitions on page 111 and be familiar with them when you come to class. So I'm going to talk very briefly about the kinematics of uniform circular motion. Kinematics means that it's moving, and uniform circular motion means that the motion is occurring in a circle with a constant radius at a constant speed. And let's talk about that for a second here. If I were to look at the instantaneous velocity of an object as it's being flung around a circle, at any given point, instantaneous velocity, what is its velocity? Its velocity is actually going to be tangential to the circle. You can kind of see that in your mind's eye if this ball was rotating round and round and round and round. At any given second, the instantaneous velocity is going to be perpendicular to its flight path. Now, we have to be careful here about the definition of speed and velocity. This speed is always going to be constant. Speed would be the length of the velocity vector. But remember that constant speed does not mean constant velocity. And the reason for that is because velocity is a vector. And this vector has changed its direction between here and here and here. So, constant speed, not constant velocity in uniform circular motion. Since we know that there is a change in velocity, that means that there must be some acceleration. Now, the book demonstrates why the acceleration needs to be in the inward direction. I'm going to leave that up to you to verify yourself why the acceleration is towards the center of the circle. It's called centripetal acceleration or radial acceleration, and it does always point to the center of the circle, and it depends on two things. It depends on how fast the object is moving, what its speed is, the velocity squared, as well as the radius of the circle right there. So, very important equation to use when considering circular motion. Now let's talk about the forces, or some of the dynamics that must be occurring with this uniform circular motion. We know that from the last slide that this object is accelerating. And if this object is accelerating, Newton's second law says there must be a force, a net force acting on it. So if we consider, a ball being, twirled around on a tabletop, so this isn't necessarily, up and down into the air. We're looking down on the table at a ball that is being, swung around radially. We know that the acceleration is going to be inward, always inward. And Newton's second law, the sum of the forces is equal to the mass times the acceleration, says that the net force here must be in the same direction as that acceleration. So drawing my ball even at another location, that says that the net force is always also going to be inwards towards the center of the circle. So if we go ahead and we write the sum of the forces is equal to the mass times the acceleration, and we draw the free body diagram for this ball, it's going to have its velocity, kind of drawing it right here, it's going to have its velocity right there. It's going to have a force inward, and I'll put an R there to say that this is radial. That is the only force acting on that guy, so I would say that the radial force must be equal to the mass times the acceleration. The book went ahead and put a subscript R there to say that that's also the radial acceleration. So here I have the radial force is equal to the mass times the velocity squared divided by the radius. So this describes the force that is needed to keep this ball in uniform circular motion. Now we can think about why this force must be inward by thinking about a ball on a string. If we think about this ball, at several different, points around this circle, and you say, let me think about what force I need to get that ball to keep on going in that circle. Let me think about, maybe not by pulling it in, but maybe let's think about by hitting it with a hammer. So here I have my ball here. In order to keep it going, inward, I need to hit that ball right here. This ball I need to hit right there. This ball I need to hit right there. This ball I need to hit right there. This ball I need to hit right here. This ball I need to hit right here. So on and so forth. All of these forces must be directed inward. So the forces are not directed outward, right? I don't want to take a hammer and be directing my force like that, because that's going to knock the ball essentially out of the circle. So forces have got to be directed inward, not outward. So just to highlight again this inward-outward force concept, the inward force, I forgot to give it a name on the last slide, is going to be the centripetal force. That is the inward force that I talked about on the last two slides. There is no such thing as an outward force, as I showed you with the hammer example on the last slide. When you hear about centrifugal forces, that's actually a fictitious force that comes from rotating inertial reference frames. That's a bit beyond what we're going to talk about for this class. So again, just to highlight why the force needs to be inwards, let's consider what happens if you have an object that is being spun around on a string and all of a sudden the string breaks. Then what's going to happen is the object is moving along, it's got some tangential velocity, kind of like that. Suddenly right here the string breaks, it has its tangential velocity, and Newton's first law would say there is no longer a force acting on this guy, therefore it is going to continue in uniform motion in the direction that it was going. No forces now. and so it goes off in that direction. For what doesn't happen right here is there is no outward force that is pushing this guy outward, so it doesn't veer off to the side like that. It has no memory of where it was. If we take a look at, say, a grinding wheel or something like that, you can see that, you know, the majority of the sparks are coming off tangential to the circle. Some of these guys up here were, you know, stuck to the grinding wheel for a little bit. They're coming off still in straight lines. Important thing here also is straight lines. It's going to fall off tangential to the circle. It's not going to follow a curved path because there is no outward force, you know, pushing this guy outward on the circle. Same type of thing applies to highway curves. When a car is going around a curve, it can even be at a constant speed. It must be accelerating. It's going to be accelerating towards the center of the circle, and there must be a net force acting on the car towards the center of the circle. So here's my car. It's going around the circle, you know, kind of like that. It's got some force. That force, if there is, you know, if it is not banked, if the road is flat, then this force must be due to friction with the tires. You can see this if you look at F1, you know, race tracks. Here we have the F1 driver that's going around a circle, or going around a curve, and we approximate, you know, this guy to be a circle, you know, of radius, or a circle with some radius right here. The racetrack driver is going to attempt to come around this turn, and if the friction force is not sufficient, then it's just like cutting the rope on the ball. The car will move nearly in a straight line, and you can see the skid marks here of where people lost contact with the road. They come off at nearly straight lines. So again, just like cutting the rope, you can see where cars had sufficient friction to maintain the radial acceleration that they needed to make the circle. They stuck to the road. So I'm going to take a look at example 5-6. I hope you're, you know, doing this as well. I expect you to be able to work problems like this when you come into class. This problem gives you a car with a mass going around a turn with a certain radius, with a certain speed of 15 meters per second, and it asks you to calculate the forces for two values of static friction. I'm going to go about it a little bit differently. I'm going to say what value of static friction is needed for this car to stick to the road. So the car is essentially, you know, coming at us here. We're in the headlights. We're like deer. It's coming around the turn. Let me draw my free body diagram for this car. I'm going to have my mass and gravity in the downward direction. I'm going to have the normal force in the upwards direction, and I'm going to draw the radial acceleration of that car. The car is accelerating in that direction as it comes around the bend here. So let me go ahead and write Newton's second law. Sum of forces in the y direction must be equal to the mass times the acceleration in the y direction. The acceleration in the y direction is 0. The car is not plummeting through the ground. Now the two forces, so I'm writing the sum of the forces here. It's going to have the normal force upwards, and then mass times gravity downwards. So adding mass times gravity to both sides, I have the normal force must be equal to the mass times gravity. Now let me do the same thing for the x direction. Sum of the forces in the x direction must be equal to the mass times the acceleration. Putting an r here now because that is the radial acceleration. The only force in that direction is going to be the radial force, which also must be due solely to friction. It's an unbanked curve. So, force of friction. Now, we know what the force of friction must be. We know that the force due to friction must be equal to mu sub s multiplied by the normal force. So I'm going to go ahead and I'm going to plug that guy in right here, and I'm going to say that the mass times the radial acceleration must be equal to mu sub s multiplied by the normal force. I know what my normal force is right here. It's simply the mass multiplied by the gravity. So and you can see that the mass is going to cancel out. So this problem actually does not depend on mass when I'm calculating for mu sub s now. Now, I don't necessarily know what the radial acceleration is, but I know that it's equal to v squared divided by the radius, and I know what the two of these guys are, so I'm going to write this now as v squared divided by the radius is equal to mu sub s multiplied by gravity, and I can divide both sides by gravity just like that, and I come up at the end of the day by saying mu sub s must be equal to v squared divided by the radius multiplied by gravity. And now I just go ahead and I plug in all the values that I know. That's going to be 15 squared divided by 50 times 9.8 meters per second squared, and we're going to come up with mu sub s must be equal to 0.46. That is the minimum mu sub s that will hold this car to this acceleration. So on highway curves, remember that the friction essentially can provide all of the centripetal acceleration. And you want to go around the turn using static friction, which is saying that your wheels are not moving at a different speed than the road. You're not slipping on the road. Once you're slipping on the road, then we're talking about kinetic friction, and that's actually bad for two reasons. The first is because the coefficient of kinetic friction is smaller than the coefficient of static friction. Therefore, the frictional force is smaller for kinetic friction than for static friction. And then the other reason why it's bad is because if you're going around a turn like that, then the static friction can point towards the center of the circle. Right, we've already shown that, we've already discussed that. But once you're using kinetic friction and you're going, say, in that direction right there, then kinetic friction is going to oppose the motion, it's going to oppose your velocity. It does not point towards the center of the circle, making it very difficult to regain control of the car and to continue along the curve, as you can see from the F1 track. Let's talk now about banked highway curves. When we were talking about unbanked, we had to use the force of friction to give us the centripetal acceleration, if we're talking about banked highway curves, we can look at our car right here and we can draw a free body diagram. This car is coming towards us, it's coming around a turn, it's accelerating in that direction right there. And if I draw all the forces on this guy, it's going to have its weight in the downwards direction, and it's going to have the normal force perpendicular to the ramp. And we can of course break these up into the normal force in the y direction and the normal force in the x direction here. Now the normal force is acting in the same direction as the acceleration. And we could also have friction acting in that direction, but if you bank the angle steep enough, then you don't need friction even at all. You would say, what is the sum of the forces in the x direction must be equal to the mass of the car multiplied by the radial acceleration. All I need would be my normal force multiplied by the sine of the angle. Knowing of course that acceleration is v squared over r, we could write this equation right here. So this is an equation that describes where no friction is required for this car to have some radial acceleration, mv squared divided by r. If we included a frictional force, put that guy right there, force of friction, right, we'd simply add that guy on right here, force of friction. Example 5.7 in your book calculates what that angle must be, given some given some velocity and radius and everything like that. Make sure you're familiar with that. Take a look at that guy and how they set that guy up. Although if you think about it, you can choose angles steeper and steeper, such that a car could handle larger and larger turns. Right, an angle like this would let a car handle a huge velocity along a along some radius. But if a car was not moving, or if a car had a low enough speed, then there wouldn't be enough frictional force to hold it to the road, so it could actually technically slip off the road. So that's why you don't see angles like this on something like highways. The last component I want to talk about with circular motion is when an object is moving in a circular path but changing its speed. That's called non-uniform circular motion. And if you think about it, that object is not just going to have a radial acceleration towards the center of the circle, but it must have a tangential acceleration right over here. So it's going to have an acceleration, a net acceleration that does not point to the center of the circle. What the radial acceleration does is that's going to change the direction. What the tangential acceleration is going to do is it's going to change the speed at which an object goes around the circle. And you can think of that, in terms of forces as not just pulling an object straight towards the center of the circle, but pulling it, in the forward direction as well. And what's going to happen is the velocity here is going to be, in that direction. The velocity over here is going to be longer. If you kind of kept it up, you could have something like that, and so on and so forth.